Welcome to the lecture number 13. So we are one third of the lectures will be covered by this. It's a 12 weeks lecture, one third means 4 weeks, right? So I hope you must be following the other lectures which have been delivered from 1 to 12. Here we are talking about processing of materials, right? In the last lecture I started that how processing of materials under different conditions or using different routes is important. That's what is we are discussing here. First let us have some recap. And the basic idea is what? Basic idea is to connect the processing with the structure. Finally, structure determines the properties of material and properties in turn determine the performance of a device. So we have discussed first the structure, crystal structure, electronic structure, microstructure. Then we talked about properties of materials. And now the last connection is the processing. That's what we are doing now. So as you see, the processing operations has three different categories. There are three different categories of processing operations. First is the shaping operation. That will alter the geometry of any starting work material. It can be solidification, it can be deformation processing, it can be even powder metallurgy or machining. That will alter the shape of the object or geometry of the starting material. Second one is what is the property enhancement operations. This is not going to alter shape, this is going to alter the physical properties or improve the physical properties, just like a coating operation or some surface treatment operation like heat treatment. And third operation is what is known as the surface processing operation. It can be to clean, to treat or to deposit some material on this exterior surface of the workpiece. In the second category, we simply apply heat treatment, where we put the sample or the component to a furnace, heat and cool and change their microstructure. We will discuss about this second type in the later part of this lecture. So shaping basically has four different types. First is the solidification processing. The starting material is a liquid or semi-liquid and then we shape it up. Second one is a particulate processing, that is starting material is basically powder and we do a powder processing. Third one is the deformation processing. The starting material is basically ductile solid like deformation using hammer or forging or rolling. And the last one is material removal, where starting material may be ductile or brittle but we remove it by machining purpose. That's something which basically sums up all the shaping processes we used to make different components. Well, this is again shown in the slide. I showed you in the last lecture also the casting, powder metallurgy, bulk deformation processes as well as machining, and there are different types. So we will discuss about each of them in a different way. So for the solidification or the casting, basically people call it as a casting process because we take a liquid, pour into a mold and make a component out of it. The starting material is basically heated to transform into a liquid or highly plastic state also possible. Many of the polymers actually are taken to the plastic state, they may not be fully liquefied. Metals are mostly liquefied and plastic molding, as I discussed, is basically a process in which highly plastic states can be achieved by heating it up. And this liquid is poured into a cavity through a pouring system like downspout, cup, downspout and the garner and get everything, and finally you solidify the liquid and get a component out of it. But that looks very simple, right? The way I talked about it. But there are many fundamental aspects need to be considered if you want to create a sound, good, usable casting. First of all, it involves many things. Solidification of material from a liquid state involves fluid flow, right? The liquid has to flow into the channels to reach the mold cavity. And then during cooling or during transformation of the liquid to solid, there will be heat transfer. And heat transfers will happen through the mold. So transfer of the heat to the mold is very important. That will dictate also how quickly you can solidify and what are the defects you can avoid. And lastly, everything, whether fluid flow or heat transfer, is influenced by the type of mold material you use. Whether you are going to use a sand, you are going to use metal mold, it will affect these processes. And one of the few things is basically this, as I showed in the last lecture, that if I cool a liquid from the liquid state to solid state and plot temperature versus time curve, so what will get? I will get a curve like this, which will show a dip in the cooling curve, and that's correspond to nucleation of a solid phase from the liquid. So you can clearly see this dip here. That dip is basically required to provide the energy to the system so that it can form nucleus or nuclei, and this dip is known as undercooling. And for the alloys, that is for the pure metals actually, or pure components, but for alloys you will not see this dip because of the phase diagram itself. I am considered a simple phase diagram where this is called length separate phase diagram between copper and nickel, and the right side you see the cooling curve, temperature versus time, and it is clear from this curve that there is no dip seen here, but does it mean the dip is not there? Well, dip is not detectable here because temperature is decreasing continuously. So this also requires nucleation of the solid phase from the liquid, and when you want to nucleate anything from the liquid phase, you need to provide energy corresponding to the interface formation between the liquid and the solid. That energy is basically coming from undercooling of the liquid below the melting temperature. So here melting temperature means the liquidus temperature, right? This is what is the melting temperature, and so you need to cool down this temperature to have nucleation. So in a nutshell, solidification is basically consisting of two processes. One is the nucleation, other one is the growth. So nucleation is nothing but formation of the crystals, or very fine crystals, or very fine clusters of atoms which are aligned or arranged in an order manner in a liquid, and growth is nothing but attachment of the atoms to this nucleus. So as you see here in this top picture A, here you see that many nuclei have formed, and there this nuclei actually are then attached to itself and forming crystal. Slowly crystal is grown, and finally when they touch each other they form boundaries, and these are called gain boundaries as shown in the D actually. So that is very simple. So solidification has two important aspects, nucleation and growth. Nucleation, as I said, is nothing but the formation of tiny stable solid particles from liquid, and this requires undercooling because undercooling provides the energy to the system for creation of the solid liquid interface, and larger the extent of undercooling, greater will be the number of nuclei. So there will be two kinds of nucleation, homogeneous, heterogeneous. In homogeneous nucleation, nuclei can form anywhere in the volume, does not require any specific sites, while heterogeneous nucleation can happen only on the mold walls or on some foreign particles, or even the surfaces of the liquid on the top, right? That is always can happen. And there are two different kinds of casting processes, expandable mold and permanent mold. Expandable mold uses sand in which you create a cavity and then pour the liquid, and liquid gets solidified very easily into the mold cavity, and then you remove this mold or dismantle the mold and take out the casting. In permanent mold it is again opposite, where you are using a permanent metallic mold in which you pour the liquid into the mold, and this mold is then solidified, and then you open up the mold and remove the casting, and you can reuse the mold again and again. That is the difference between permanent and the expandable mold. And one of the most important expandable molding process, green sand molding, you can actually create a mold cavity and pour the liquid and form the casting very easily. Let us talk about few other important inverse casting processes. One is the investment casting process, which is used to create integrate shape castings like statue, or even many other integrate shape castings which are available in the market, and this is done using by wax pattern, and basically wax pattern is dipped into a slurry to form a layer of slurry, and after that some sand basically pour into this slurry, pour into this coated slurry onto this wax mold, and this process can continue for several times. Finally this whole thing is put in the furnace at high temperature so that the wax is melted away, leaving behind the shell of the mold, and in this way you can create any shape you want, any integrated shape you want, and this then further mold is used for pouring of liquid and formation of casting. This is the investment casting process. You can have pressure die casting process, either low pressure or normal pressure, high pressure. Basically, this is the metallic mold, a permanent mold casting process. You can pour the liquid or push the liquid into the casting cavity or mold cavity, sorry, and then allow this to solidify first, because the mold is metallic one. So pressure die casting is again same. Here you are applying a pressure to push the liquid into the cavity. That is the difference between low pressure and high pressure. Squeeze casting again similar, in which you are applying a punch to squeeze the liquid into the cavity. That is what the difference. Instead of applying a pressure directly, you are putting a punch and the pressure is applied to the liquid by the punch. Now you must have seen many pipes on the roadside, right, where these pipes are used to carry water. Have you ever imagined how these pipes are produced? Well, they are produced by centrifugal casting. What is centrifugal casting? Well, it uses the concept of centrifugal force. What is that? You clearly see this is the mold cavity, right? And you can see here, this is the mold cavity, you can see there. Now this cavity is rotated at a high RPM. At the same time, liquid is poured into this cavity. So if you have a liquid and you pour rotating this mold at high RPM, okay, 1000 or maybe 1500 RPM. So because of the centrifugal force, liquid will be filling the outer layer or the inner layer of this mold. Correct? That is what you see here. It is filling the inner layer of the mold. You can see this very clearly. So now this rotation will allow, speed of rotation will allow thickness or formation of the thick or thin layers of this layer, all this thing or the metal actually onto the inside this mold cavity. After that you allow it to solidify, because the mold is a metallic mold. So heat transfer is faster here compared to the sand mold, and then once it is cooled you form a nice pipe. So centrifugal casting can be used for many other purposes, okay. Metal mold, this is very actually useful one. You can actually using extractive metals, refractory metals or reactive metals, everything can be cast and to give this shape. This technique is used to produce relatively long hollow objects without need of any cores. Remember last class I told you about the cores which has to be fitted inside the sand mold. Here you do not need that, you can create easily this kind of casting. Well, another important technique in the literature is called a continuous casting, which is widely used for steels, aluminium, copper, many other metals, and it is a continually casting process. What is done here? Let us be shown in this picture. You can clearly see there is a ladle which contains liquid steel here, and then from the ladle liquid steel goes into the turn dish. Turn dish is nothing but a reservoir, and then from reservoir this metal or liquid steel is passed on to a copper mold, open copper mold. This copper mold is water cooled, and as this metal goes through this long copper mold, outside layer of this liquid will solidify or frozen and forming a thin solid layer. Inside it will be still liquid, and then slowly it is ejected from that mold and by these rollers, actually support rolls, and so that it can be bent easily because it is still semi liquid state, right. Only outer layer is frozen because of the water cooled copper mold that has taken out the heat from this liquid outer layer, and then slowly it is also cooled by secondary cooling system like water spray, and finally once it comes out it becomes completely a solid, and this it can be cut into pieces and used. Since it is done continuously, it is called a continuous casting process. I would like to show you in much detail of this process because this is one of the wonderful process which is adopted by the industry, or it is a major discovery in the field of materials and metallurgical engineering. As you see here, this is the liquid steel which is inside a ladle, and then it is poured into a container or reservoir. A reservoir is what? Reservoir is basically a turn dish, we call it a turn dish. And this is the copper mold which is shown as by blue color, and the zoom version of this area is shown here. This is the copper mold you can see, and the copper mold, when this liquid goes through the copper mold, only the surface layer is frozen, forming a thin layer on the surface, and this thin layer of surface basically is holding the inside liquid, and then finally by rollers the whole thing is bent and subjected to a further cooling. That is what I discussed in the last slide, and this is a better view how the liquid is transferred from the turn dish. You can have two turn dish also system You clearly see that, correct? Or you can have multiple tandem system as possible also. This kind of geometry used when you have to have large production capability of the furnace. The last thing I talk about in formation of the casting or solidification is the single crystal blades. Remember I talked about these blades for the superalloys, right? You can go back to my earlier lectures and you can see that. But how these are produced? Well, this again produced by casting route. So let's discuss about that. Basic concept is very simple. If you have a liquid, let's say, and put on a chill plate can be copper plate actually, water cooled copper plate, and then what will happen? From this bottom side of this liquid, the columnar crystals will grow. Well, why the columnar crystals go? That's very simple, because heat transfer is happening vertically, right? The chill plate will take out the heat vertically. That's why these columnar crystals will grow. Now these columnar crystals, as they grow, you can do a very engineering. What you can do, you can create this kind of a constriction. Can you see this constriction very easily? This kind of constriction. This is a typical or very odd shape of constrictions. This constriction, only one of the columnar crystals to pass through. Other columnar crystal will not be able to pass through. Rather, they will die out, they will join this columnar crystal. Since one crystal has gone through, then it will come out from this constriction and and grow. It will grow by the mass transfer from the other columnar crystals, right? So you can clearly see on the right side there is a picture. Very clearly you can see the right side there is a picture, and this is the constriction, correct? Very complicated shape. Because of this constriction, one particular crystal grows through. The thickness of the inside thickness constriction is very, very small. That is the order of the thickness of the crystal. That is what is used. So this is how the single crystal blades are manufactured. Remember, this is a grown up technology. Single crystals are used in the turbine engines, which are used for the planes. So that is a very wonderful technology which is used worldwide to produce single crystal blades. Now we are going to the second processing operation, the processing operation which can enhance the property. They can improve the physical properties without changing the shape of that. What is that? I talked about it, right? That this is nothing but a heat treatment process. And many of the cases, the after casting, the components are heat treated, many actually. Examples are the industry. The components are produced by casting route, and they are subject to heat treatments to relieve stress, to improve the properties, or to even create different microstructure. Many reasons are there. So how do you explain that? Well, there are many heat treatment processes available in the literature, and I cannot discuss everything because of the time constraint and because of everything. You can even read some of my own courses like phase transformation materials, phase diagrams materials available on NPTEL, and try to understand that. This is a typical iron carbon phase diagram. Concentrate on this part of the phase diagram, okay, not the top part, the steel part, okay. So where you see that there is a phase called austenite, which is nothing but FCC, and there is a phase called alpha, which is alpha ferrite, or which is a BCC, and there is a phase called cementite, which is nothing but Fe3C. And there is a reaction here at this point, at this temperature 723 or 723 to 738, does not matter, because this is taken from Calvert, the temperatures can vary. So normally we consider 723 degrees Celsius temperature, and what can happen at this temperature? At this temperature you see the gamma, which is FCC phase, is transformed into alpha, which is a BCC phase, plus Fe3C. This is called eutectoid reaction. Right, in the literature. Now all the heat treatments for this steels are basically based on altering this reaction. We will talk about it. Let us say I start with austenite. Austenite is single phase FCC structure, single phase FCC, we call it gamma, and depending on different cooling conditions, you can change the phases. Suppose if you cool it slowly, this will transform to perlite. Perlite is nothing but alpha iron, alpha plus Fe3C. So this is basically forming like this, gamma going to alpha plus cementite. That is what I told you, right, in the last slide. But if you cool it fast, it will form martensite, which is body center tetragon structure, a distorted BCC structure, very hard, strong, and material, and in the last case if you cool it intermediately between cooling rate for formation of perlite and martensite, you will form benite. Benite is nothing but a, you see the feathery kind of things, and inside which you have again alpha plus cementite. So, benite and perlite are morphologically different. Perlite formed because of the diffusion process separating the carbon out from the gamma iron, correct. That is what the gamma iron contain lot of iron, carbon, and once you transform that, gamma iron, alpha iron becomes very lean in carbon and all the carbon goes into carbide. That is what is called a perlite. So, now austenite to perlite is basically a diffusion control reaction and it forms a lamellar structure consisting of alpha and Fe3C. Very simple, you can clearly see that. Well, this is can be seen in a TM also, and you can see that these are the lamellae of alpha iron and perlite. Black colors are basically cementite and this is the alpha iron. So, they forms a very nice simple structure. So, now how do we can explain this heat treatment process? That can be easily explained by TTT diagram. TTT means T for 1 T is for temperature, 1 T is for temperature, second T is for time and third T is for transformation. So, as you can see here, time is plotted as a log scale because time can vary from few seconds to few days, and temperature is shown like this on Celsius scale. Now, what you see here, these are the different cooling curves because time and temperature, right, and now this is the diagram. You can see here this is austenite or gamma, and then this is basically perlite and this is basically benite. I write B for benite, P for perlite. So, if you cool it slowly, this austenite will transform to perlite. If you cool it and hold it back like this, it will form benite. But if you cool it further, whatever remaining austenite will be there, that is transformed to martensite. That is done by wild quenching. Wild quenching can produce both perlite and martensite. This is what is written here, martensite, but is not seen properly. And but if you cool it very fast, like water quenching or brine water quenching or ice quenching or liquid nitrogen quenching, whatever, you can produce martensite completely. So, simply by doing this heat treatment process, I can generate different kind of microstructure, and this different kind of microstructure can give us different set of properties, which is shown in the next slide. You can see here, this is for some other steel, okay, not the one which I shown you there. Here you can clearly see it is shown nicely cooling. This one is produced alpha plus perlite. This is basically not a, this steel is basically for 0.8% 8% carbon steel, okay, that is nothing but eutectoide steel. But this one is hypo-eutectoide steel, composition is less than 0.8% carbon. So, here you can see you can produce alpha plus perlite. If you cool it slowly, you can produce benite. If you cool it fast, you can produce martensites. And this is what is shown as the hardness. Martensite is the highest hardness, this is the Rockwell scale, perlite is the lowest hardness, right. So, and here shows the mechanical properties. Okay, if I take different conditions of the same steel, anneal it, I produce perlite. If I normalize it, I produce still perlite, but finer lamellar spacing, finer thickness of those slabs I shown you. And if you produce quench, you produce martensite, you have very strong, very high strain, but almost no strain or no ductility. If you produce in between quench and tempered, you can get good combination of strength and ductility. Here you can actually temper the martensite. I do not want to go in details of that, but you can read this book by Afner, Introduction to Physical Metallurgy, very widely available in the bookstores. Well, other than that, we can also do what is called case hardening. Let us take up the gears, okay. You can see that these are the spur gear, these are bevel gear, okay. And these gears actually, this is a pinion, These gears actually rotate at high speed in a car or in a train or in many other devices. So when they rotate at high speed, the teeth of the gear undergoes a lot of wear and tear. So how do we take care of that? Well, this can be taken care very easily. This is what is shown here. You can see the tooth has failed here, and you can see here the wear and tear of the teeth. So sometimes even you have internal cracks can be formed in the surface. So how to take care of this kind of things? So we'll discuss about this thing in the next part of this lecture, part 2 of lecture 13.